Right, so we're ready to start. Welcome everyone to the first webinar by Cloud Native Computing Foundation in 2018 that is focused on the newest release of Kubernetes that went live publicly in December, around 1 month ago. It's Kubernetes 1.9. And today we have a group of people who been developing the new features and developing the new functionality for Kubernetes 1.9 release. My name is Ihor Dvoretsky. I'm a developer advocate at CNCF, and I've been a features lead at Kubernetes 1.9 release. Also, I am a co-lead of SIG product management at Kubernetes community. Together with me, we have Saad Ali from Google, who is a SIG storage lead, David Eads from Red Hat, who is a SIG API machinery lead, Michael from Apprenda, leading SIG Windows, and Kenneth Owens from Google, who is primarily responsible for driving SIG apps. So today we'll speak with you about the highlights of Kubernetes 1.9 release, why this release is so exciting for Kubernetes people and for Kubernetes community. And today we'll also highlight a group of new features and major features that have appeared in this release. First of all, it's the container storage interface called CSI, and Saad will describe it with more details. We have the new webhook admission feature that will be described by David Hitz today. Windows Server Support is amazing new feature in this release, and so many people were waiting for it for a long period of time, and Michael will describe this feature. And workloads API has appeared as the general availability feature, and Kenneth Owens will be a person who will describe this feature today. And we'll also have the Q&A session at the end of the webinar if you'll have some extra new questions. So first of all, a few highlights about this release. As I mentioned before, it's the final release in 2017. We had four releases in a row in the previous year, starting from 1.6, and Kubernetes 1.5 was the final one, and probably the most important one to close the four rows for releases in that year. And Kubernetes 1.9 was a really important release for the community because we have almost switched from the model when all the features are dictated from some central point. At the same time, with Kubernetes 1.9 release, we have the amazing practice when every single special interest group, every single community, sub-community within the Kubernetes community that's responsible for some technical area, they are responsible for delivering the new features, and they define the roadmap and the vision, what exactly they would like to see in this release. We had almost 40 new features. Most of them have been delivered as the alpha features. Alpha feature means that it's extremely new. It's the first time when it appears to the world, and everybody can try it in the new release. At the same time, alpha feature is not enabled by default, so be careful about enable alpha features in your Kubernetes cluster. At the same time, if you'd like to try some extremely new functionality, alpha features are for you. Some features were delivered as beta features. Beta feature provides some extra stability compared to alpha feature. It's not targeted to the real production environments as the stable features. But if you are going to enable some new functionality in your Kubernetes clusters and targeting some new functionality for your workloads based on Kubernetes, please take a look at the beta features. And the stable features are dead features that are really intended for the real production usage. And some of the features that we'll describe today are the real stable features, or GA, you may also hear this definition. So speaking about the major areas where Kubernetes 1.9 features were delivered and developed, Kubernetes community was primarily focused on enabling extra workload support and enhancing the existing workload support. enabling and extending their capabilities in terms of security. Kubernetes 1.9 was really focused on the extensibility features together with the storage features, and all these major areas will be described today by our speakers. So now I'd like to invite Saad Ali from Google, who is co-leading SIG storage, and he'll share his highlights on the container storage interface, or CSI.
All right, thanks a lot, Ihor. So first of all, SIG storage worked on a number of features this quarter. They all went to alpha. Notable features include block support, sizing support, making the scheduler aware of storage, which is very important for local storage, and then finally, container storage interface. While all of these features are big, today I wanted to focus in on CSI in particular. And with that, let's go to the next slide. So let's set the stage. What is the problem that we are trying to solve with CSI? Kubernetes already has a very robust volume plugin system. It's unique and very powerful. It's the first to allow workloads to dynamically provision storage as needed instead of expecting the storage to be pre-provisioned. And while it's very powerful and great for our end users, it's a little bit of a pain to maintain because adding in new volume plugins requires code the Kubernetes repository. For vendors, they don't like to do this because it means being tied to the Kubernetes release cycle. It means that they have to open source their code, whereas some vendors don't want to do that. And it's bad for Kubernetes in general because it makes us responsible for testing and maintaining external code and for a number of reasons. So we want to get away from these entry volume plugins, and let's move on to the next slide. So one of the first approaches that we had to moving out of tree was flex volume. It was experimental initially. Basically what we did was take the internal volume interface and extend it by saying, you know, the primary interface calls that we have, let's just go ahead and call out to external scripts that'll fulfill that. And so basically the way that you deploy a new volume plugin would be you write a script or some executable and you deploy that on your node machines. And then Kubernetes discovers them and allows you to use them. This approach works, but it has some problems. One of the primary problems is that deployment is pretty painful. You actually have to have access to the root file system to be able to deploy new volume drivers. And it doesn't really answer the question about dependencies, right? If you're deploying a executable directly to a node machine, the dependency, the binary may have dependencies that are not already on the host machine that you also have to install. Things like mount tools, file system tools. Ultimately, what we want to be able to do is get away from that model and be containerized so that you could very deploy new volume plugins and all their dependencies. So this is a problem that we're not alone in facing. We talked to other container orchestration systems who experience the same issue. And many of the storage providers also were experiencing this to the point of trying to invent a solution for it. And so what we did was get together and create this new initiative called the Container Storage Interface. The hope is that it would become an industry standard such that these different container orchestration systems all support it and can expose a wide variety of storage systems to their end users. And it's great for storage vendors because they can write a single volume plugin and have it exposed to as many users as possible. Next slide. So again, this collaboration between Kubernetes, Mesos, Docker, and Cloud Foundry, we're all trying to solve the same set of problems on how to standardize creating new storage volume plugins. Next slide. So what is CSI? It's essentially three main method calls. One is to create a volume or delete a volume. Another is to attach or detach a volume from a node. And finally, to mount or unmount a volume. What CSI is not is a specification that specifies packaging or deployment. The CSI specification only defines the interface with which arbitrary CO can speak to an arbitrary volume plugin. It doesn't care how the volume plugin is packaged, how it's deployed, how it's monitored, et cetera, et cetera. Basically, all it wants is RPC input that talk. Next slide. Can we go to there we go. So the current status of the CSI spec is that in December 2017, we published the 0.1 version of the spec, and the various COs have started implementing their versions of this spec. And we introduced alpha support for this spec in 1.9 Kubernetes. Next slide. So the way that we introduced it in Kubernetes is actually a new in-tree volume plugin, very similar to Flex. So if you're familiar with Flex, think the same thing for CSI. The nice thing about adding an in-tree volume plugin is that we can reuse all the existing volume code without having to modify any of the core or potentially destabilizing the existing code. And another nice thing about it is that as far as the users are concerned, they're going to be interacting with CSI in exactly the same way they've become used to interacting with many of the entry volume plugins. That means using storage API primitives like persistent volume claims, persistent volumes, and storage classes. Next slide. So I'm going to walk through really quickly what that would look like to an end user, to an application developer who's trying to deploy their application on Kubernetes. So first thing is they want to dynamically provision a volume. So their cluster administrator would come along and they would create a storage class. Normally this provisioner would point to one of the in-tree volume plugins, but now we support out-of-tree volume plugins. So the provisioner can be, for example, in this case, CSI driver by com.example team. And parameters is just an opaque set of parameters that should be passed to that driver when provisioning is. So this is how the cluster administrator enables dynamic provisioning for this particular driver. Next slide. Okay, so now as a end user, first of all, they're going to create a persistent volume claim, which is basically a request for storage. They define what their minimum storage requirements are in terms of how much space they need, what the access modes are, but they can also specify the storage class, in this case, fast storage, which corresponds to the external CSI driver. And when this persistent volume claim is created, Kubernetes will automatically go out and call out to the external CSI driver to provision this volume and create a persistent volume object to represent it. Next slide. And then finally, you can now use this persistent volume claim inside their pod definition, just as they have in the past, by referencing it as a persistent volume claim volume. Next slide. So there's a whole aspect of how to deploy CSI volume drivers on an arbitrary Kubernetes system. I'm not going to go into that. There's a blog post coming out tomorrow which links to documentation. Feel free to take a look at that. Otherwise, this will run on a lot longer. But very quickly, I wanted to highlight where we're going next. We just launched alpha for CSI last quarter. This quarter, we're trying to decide whether to go to beta, or if we have too much work, we're going to remain in alpha and go to beta next quarter. We're trying to make that decision within the next few weeks. On the CSI spec side of things, we are going to take the learnings from actually implementing this on the CO side and actually implementing drivers to improve and revise the spec and push it to 1.0. We want to also focus on improving how we handle topology. This includes things like zones and regions. And we also want to be able to improve how credentials are passed in through the CSI interface. And then finally, we want to figure out what the certification story would be for a CSI driver. How does a arbitrary CSI driver get the stamp of approval to say that this is compatible with the CSI interface? So we have a lot of work coming up in the next few quarters. If you're interested in joining us, please join us in the storage SIG. We're looking for volunteers who are interested in this space to help us out. And that's it. Thank you.
All right, thank you, Saad. So I hope information about CSI and how Kubernetes handles the storage questions was really useful. So now I'd like to welcome David, who will describe his insights on the webhook admission feature.
Great. Next slide, please. So in Kube 1.9, we moved webhook admission to beta. I'm going to briefly describe what admission is. So admission is a phase of REST handling when you submit an API object that comes after authorization, but before you persist the data to etcd. Admission plugins have access to the actual content of the body itself. So if a user submits a pod, an admission plugin can actually look and see the content of that pod. And this means that an admission plugin can have semantic knowledge of particular resource types. It can know what a pod image field means or what a cluster role rule means. Admission is split into two phases in this diagram. You can see we come in, we have authentication and authorization. Then there's a phase where admission is allowed to mutate data that the user sent. Then there's a schema validation, and then there's a phase where admission gets to validate the final object before it is persisted to etcd. If we can go to the next slide, I'll explain those in more detail. So mutation is where an admission plugin gets a chance to actually change the resource content itself. So a user can submit an object and say, I want to run image foo, but an admission plugin come in and say, no, you don't really mean foo, you mean something else. It can add labels and annotations. It can change the resource in any way it wants during mutation. Even after mutation is done, there's still a chance for, there's still a chance for validation. Validation is a spot that runs after all mutation is completed, and it gives you a chance to enforce the invariance for an API resource. So regardless of what a user entered or what the schema validation says or what has been mutated by an admission plugin, a validating admission plugin can look and say, the final result of the service account field must have a value. Or does a user have the power to set a particular field to a particular value before it gets persisted into etcd? These invariants can be really useful. Next slide, please. So why webhooks? We had admission for quite a while. It was all done in tree, and being in tree really restricted its utility. It meant that installers or deployment mechanisms were unable to add admission plugins into an API server without recompiling it, and very few people wanted to do that. And now that it's a webhook, there's a lot of example uses, right? You could do things like inject a sidecar container. It's something that Istio was looking at. You can do things like forcefully resolve image tags to SHAs, which is very helpful for repeatability, and this would let you do it on all sorts of resources that contain pod specs. And it's also useful for things like complex custom resource validation, right? If you want to be able to say, this field can only be set if this other field is set to something between 6 and 7. So I have a brief demo next that shows actually wiring this together. So let's go ahead and do that. Thanks. I've started with a cluster that has aggregation enabled, and I'm going to self-host my admission webhook on the cluster. To start, I'll show you the basic resource manifest. It's simple. It's got a daemon set that runs the server. And further down, I have an API service that exposes it via aggregation. It allows me to use the in-cluster authentication and authorization to secure it, and it allows me to use kube control to test whether my webhook is behaving the way I expect or not. Down just a little bit further, I have the validating webhook configuration. This is the object that's new to beta in 1.9. It has a stanza that describes how to connect to your webhook, and right there. And then it has a bit that choosing what to do if the connection fails and the server can't make contact. In this case, it says to fail. It also has a list of rules for when to make a call out to the webhook. And this one says, call the webhook if you're going to create a namespace. So I have a little script that has some glue to create some certificates and runs apply. So I'm going to install that right here. And after doing this, I can actually test my webhook admission using kube control. So I have an API object that exactly matches what an API server would send. This one is testing a create on namespaces, and the namespace name is deads. I can use kube control to submit this, and then we can look at the response, and the response says that the request is allowed. With this admission server, if you reserve a namespace by creating a particular custom resource, it will prevent the request from succeeding. So I am going to create the custom resource that reserves it. And now if I run the same check we ran above, again using kube control to test my webhook, we will be able to see that deads is reserved, and the request overall is forbidden. And what this will mean is that when the API server runs it, it'll fail. Now, I said this was all secured by RBAC. If we actually try to run that same command with kube control as another user like deads, and you can see me doing it right here, you'll get a forbidden error. The API server said, nope, you're forbidden. You aren't allowed to hit the webhook admission server. In order to grant access, you do it like anything else with RBAC. You're going to create a cluster role binding, granting access to the webhook. The role to grant access was created when I ran that apply a while back. And so I'm going to add deads. And now if we run the check again, we're going to be see that we're allowed, and we will get the same result as when we ran it with cluster admin. So we gave permission using RBAC. We could take it back again with RBAC if we like. So you can use it to manage access. Now that final bit, we can try to create the namespace, and we can see here that the webhook admission server named namespace reservation denied the request because the name is reserved. So that's how you can wire everything up using a self-hosted webhook admission server. You get in-cluster security for free, and it works with no config from the Kube API server and from any extension API server that you want to connect from. So we can jump back to the slides. And I have a picture describing what we actually built here. So you can see that we have a client. Any client, kube control or some other client, comes in as the user. It goes to the Kubernetes API server. And the API server, if you have aggregation, might proxy to an extension API server. And that can loop back using a service account credential to the Kube API server, which will then securely proxy to the webhook admission server. And what this allows you to do is it allows you to identify in the webhook admission server what API server is contacting you and decide whether it has access or not. And all this wiring, all the credentials that are used can be done automatically and safely without any config on your part. And doesn't require any credential distribution mechanism, and it will work on any API server that supports aggregation. So if we go to the next slide, I have just a brief summary that gives you the benefits, right? You can test it with kube control, you automatically secure it with RBAC rules, and it works for all kinds of servers. Other topologies are possible to build, but when you build them, you need to be careful about inventing credential distribution mechanisms. They're very hard to maintain. The biggest fear with aggregating an API server is it's scary. There's a lot of options, and people get very concerned about it. So on the next slide, I have, I hate when people put code in slides, but I had to do it here because this is the code that you need to create your own admission webhook. It's 3 functions. You have 3 functions, and then you don't even have to wire the command. You don't wire the flags. You don't have to wire any of the pieces is just your business logic. It's where do you want to host it? It is what am I going to do to validate an admission request? Is it going to be, it's your chance for thumbs up, thumbs down, and a function to initialize it. And so this is all built on a couple libraries that I linked in. There's a generic admission server library, which is built on the Kube API server library. And then a full working example that you saw here today. And there's some stuff lighting up at the bottom here, so I suspect there are questions. I'm dense. I do apologize for the density of the information. There is a lot here. And hopefully it will make sense. You can reach out to me on Slack. I'm in API Machinery as Deads2K. So if there are no other questions, I will hand it over.
Thank you, David. So now we have the Windows Server section, and Michael will take lead on this.
Thank you, Igor. Hi, everybody. Next slide, please. So the SIG Windows community has been working very hard for close to 2 years now in basically bringing Windows Server to the entire Kubernetes ecosystem. That essentially our goal here is to significantly expand the implementation scenarios and the enterprise reach of Kubernetes. Gartner estimates that about 80% of enterprise applications today still run on Windows. So by bringing .NET and Windows-based applications into Kubernetes, it allows many enterprises that have adopted a hybrid model where they have both .NET, Java, and other programming languages to manage all of them in a cloud-native way using Kubernetes. That enables ASP.NET, .NET Core, IIS, Windows services, and many more applications to be hosted on Kubernetes, and allowing Kubernetes to become the best cross-platform heterogeneous cluster manager. All of that work obviously would not be possible without the hard effort from Microsoft in investments into Windows Server containers, container networking, and other features that enable us to get here so far. Next slide, please. From a timeline perspective, we released alpha support with Kubernetes version 1.5 last December. And then 1 year later with 1.9, we released beta support. Alpha support was mainly great for proof of concept projects and visualizing the roadmap and allowing everybody to understand where we're going with Windows containers in Kubernetes. Now with beta and our continuous feature and functional advancements, both in Kubernetes as well as in Windows Server itself, now you can take advantage of that work and you can have production level workloads running on Windows Server with Kubernetes. Our goal is to go to general availability sometime later this year, probably towards the end of the first half of 2018. Next slide, please. Now, from a feature perspective, we're very excited about the set of features that we're bringing into the community with this release. We have improved support for pods. In the past, you could only run one single container per pod. Now we've done a lot of work, both in Windows Server and in the containers perspective, so that you can have a pod that can share the network namespace using networking compartments with multiple containers. This kind of brings the feature of a pod in parity between Windows Server and Linux-based containers. We've also reduced the networking complexity by using a single network endpoint per pod. We've moved the load balancing from user mode to kernel-based using their virtual filtering platform called VFP that's using the Hyper-V switch extension. We've done work to incorporate CRI, pod, and node level statistics. So that means now you can get profile data out of your Windows Server containers, and you can use the horizontal pod autoscaling to autoscale your containers using these performance metrics. We've added support for kubeadm. So if you're using kubeadm to simplify the provisioning of your entire Kubernetes cluster, now it has support for Windows Server, and you can use a single tool to deploy your Kubernetes infrastructure. And last but not least, we've added support for config maps, secrets, as well as volumes. These are key features that allow you to separate, in some cases, secure the configuration of your containers across different Kubernetes clusters. Next slide, please. But one of the biggest features that we had in this release, and the reason why we are in beta, is the networking enhancements and the CNI plugins that we've brought into the community. We have an upstream L3 routing plugin. We have the host gateway with IP routes configured on each host. And then we have the Open vSwitch and Open Virtual Network, also called OVN OVS, with overlay that supports STT and the Geneve tunneling types. And there's a lot more network plugins and enhancements that are under development, and we'll be able to bring them to the community within the next few months. Some of those include the WIN overlay that will enable VXLAN and IP and IP encapsulation with Flannel. We will have a Windows L2 bridge or host gateway CNI that will come out. And we'll also have OVN using cloud networking without overlays that will also be released fairly soon. Next slide, please. So in the last few months, probably a little bit over a year, we've been very busy. As you can see here, this is a fairly busy slide. So you can see that at different point of intervals, different features that we brought in, from the CRI to config maps and secrets to the CNI plugins. And the community is working very hard in continuing down this path, continuing to improve our support for Windows, adding more CNI plugins to deliver customers choice and allow them to have a unified networking configuration and infrastructure between Linux-based containers and Windows Server containers. We'll also add support in the future for Hyper-V isolation, stateful send functionality, as well as support for Kubernetes network policies in OVN Kubernetes. Next slide, please. Now, what I want to do is I want to show you guys a little bit of a demo, show you a little bit of OVN OVS on Windows, config map secrets, and routing and load balancing. One of the things I want to show is the multiple containers per pod, but that's, if you guys come and talk to us in the community, we can show you guys how to use it. Look at our documentation, but that's something that's definitely out there. Now I'm using OVN and OVS for this demo. This particular architecture has a lot of advantages. You know, you get distributed firewalling, you get the cross-cloud communication using Geneve, you can get load balancing north-south and east-west for on-prem environments, as well as distributed DNS. So let's go ahead and look at that. I'll go ahead and share my screen here. And I'm RDP'd into one of my Windows environments, and what you're looking at here is my kubectl running on my Kubernetes master. So if I do a get nodes here, I have 3 nodes in my environment, 2 Windows nodes. One of them is running Windows Server 2016, the release version. The other one is running RS3, also known 1709. And then I have my Linux node as well. And if I use JQ here to give me a little bit better visualization, you see that I have my first 2 nodes are tagged with Windows as the operating system for Kubernetes, and the last one is Linux. So I do have an environment here with multiple types of operating systems. So let's go ahead and get our pods here. So I have a few pods already deployed. I have Guestbook, I have an Apache IIS and Nginx pod, and I have some Redis nodes as well. And these are split into 2 services. One of them is called the Apache service, and the other one is called Guestbook. So let's look at Guestbook here for a second. So notice here that my cluster IP is .9.202. So if we come over here, the Guestbook is up and running. And I can click on environment, and a couple of things that are noticeable is I have my 2 config maps here. Hello attendees, glad to be here. And then we also have a secret here as well. So not very valuable secret, this is just a secret, but we can show you guys here that we have both config maps and secrets running, so you can take advantage of them in Windows Server containers. If we try to look into the container itself, under the data folder, we have a volume that was mapped to the container, and I can look at the files here that were residing on the host operating system, and they were mapped directly into the Windows Server container. Now the actual YAML file for this is basically very similar to the ones that you're familiar and writing today on Kubernetes. So we have the secret and config map that I defined earlier. And then our pod specification is very similar to what you see in Linux, with the only difference is that it's targeting the operating system to be Windows Server in the labels. So if you look at the node selector at the end, it's targeting Windows, and that's what's telling Kubernetes to go ahead and deploy this to a Windows environment. I also have one more service here, and that's my Apache service. And that service has deployed 3 pods, an Nginx pod, an IIS pod, and an Apache pod. And if I open it up here on, I can see that if I hit the IP address for my service, I get IIS. If I refresh it again, I get Apache, and so on and so forth. So I went ahead and created a simple PowerShell script here that will make 20 calls against that exact IP address. Let me know what kind of results it gets. So you can see here, we're load balancing across the different endpoints and the different pods that are part of this service. And we have Nginx, IIS, and Apache all routing against the same service. So this was a short demo, but I wanted to just give you guys a little bit of a brief sneak peek into what's possible with Windows Server containers. I'm hoping that you guys can come and join us in the SIG Windows Slack channel, post questions, try out the work that we've done, and file bugs, or even come in and help us fix them and get us to GA. Thank you.
Thank you, Michael. So the next feature is not a single feature, it's the group of features under the single umbrella. And if you remember at the beginning of our webinar, I've mentioned that some of the features are finally being presented to the GA stage or stable stage. And the next group of features is actually that group of features that is finally stable in Kubernetes 1.9. With Wenkel Ken, who will describe the workloads API for Kubernetes, starting from Kubernetes 1.9.
Hi, I'm Ken Owens, software engineer at Google and co-lead of the SIG apps. Slide, please. So in the beginning of Kubernetes, pods were pretty much all we had. And it's basically a small group of containers and volumes. I'm pretty sure most of you in the audience are familiar with what a pod is. The picture over on the right is basically the most basic pod you can have that has 2 containers. It's a file puller with a web server. And the idea would be you'd have a pod where one of the containers pulls down files and stands up a web server that serves static content. Slide. Well, pods weren't really enough for most users. I mean, honestly, manually creating a ton of pods individually probably isn't what you'd want to do. We really wanted to be able to seamlessly and reproducibly create many pods that are identical. So then we developed the Replication Controller. Replication Controller does precisely that. It creates n identical pods. These pods are fungible, meaning creation for these pods doesn't have any implied order, and the pods don't have any actual identity. In fact, the identity is a random, hash-based identifier. You can scale a replication controller, but you can't do things like rolling updates, rollbacks, and rollovers. Slide. So replication controller eventually evolved into replica set. The main difference there was just we added set-based label selectors. Other than that, they're pretty much identical. Slide. So as we were talking about previously, what users really wanted to do was to be able to orchestrate those pods. They wanted to be able to do things like have sequential rollouts, have blue-green rollouts, roll back to a previously known good version, or potentially roll forward, which would be like a rollover. So we developed deployment, and that actually came out of deployment config from OpenShift and got upstreamed into main Kubernetes as deployment. Now, by the time deployment came out in extensions v1 beta 1, the only 2 v1 API objects you had for workloads were replication controller and pod. And at this point, we didn't actually recommend using replication controller. We recommended using deployments and replica sets, and replica sets only as an implementation detail of deployment. That left people in a kind of weird state because on one hand, you want to use the most stable API version, you want to use v1 GA objects. On the other hand, we're not really contributing or upgrading any of the existing objects, and we're encouraging you to use beta objects. Slide. So about this time, people wanted the same type of features for deployments and their stateless, like 12-factor apps for cluster add-ons, local shared sidecars, data nodes for distributed file systems. And they wanted the same type of seamless rolling updates, rollbacks, and rollovers that you get with deployments. So we came up with Daemon set. A Daemon set is basically what you use when, instead of wanting exactly n replicas of a pod or about n replicas of a pod, you want to attach a pod to a particular node anytime the node enters a cluster. By the time Daemon set it came out, we had also added that to extensions v1 beta 1. It elevated to beta fairly rapidly, but again, it still wasn't GA. Slide, please. So lastly, we wanted to be able to orchestrate stateful applications, in particular, things like relational database management systems, distributed key value stores, message queues like Rabbit, distributed log structured storage like Kafka, key value storage like etcd and Zookeeper. These types of applications required a different set of semantics than were generally available with replica sets or deployments. They needed a stable network address in a lot of cases. The pods had identities that needed to survive restart, and they needed stable storage. Like they needed a durable PV or PVC that got attached to the pod and would get reattached anytime you restarted the pod. So we came up with stateful sets. Slide. So we were done, right? Like we could orchestrate all the things. We were ready to, take over the world, and all of your workloads could run on Kubernetes. Well, sort of at least. Slide. Well, software is never done. And by the time we had actually gotten deployment, daemon set, replica set, and stateful set out there and at a beta level of stability, they were spread across 3 different API groups. There were many inconsistencies in terms of like what rolling update looked like, what the statuses looked like. And primarily the issue was everything is beta. And like, honestly speaking, in Kubernetes, things can maintain beta level of stability for a long period of time. And it doesn't mean you shouldn't use them. It doesn't mean that they're not stable enough to use in a production environment in all cases. But many people aren't going to be comfortable using something that's beta in a prod environment. And honestly, people want to be able to build against a stable API if it's going to be a production software system. Slide. So in Kubernetes 1.8 and 1.9, we started the path to move everything to GA. We took daemon set, stateful set, deployment, and replica set, and moved them into the apps v1 beta 2 API. The reason we primarily did this was to allow us to break things in a backward incompatible way so that we could fix things that we knew were deficient with the API prior to taking it to GA. Some of the bigger things is selector defaulting. I don't know if people remember this or are aware of it, but previously, if you created a deployment and you didn't give it a selector, it would generate a selector based upon the labels that are associated with the pod. This caused no end of havoc with kubectl apply. In general, we found that defaulting the value of any field in the object off of another field is pretty much an anti-pattern for kubectl apply. So we got rid of that. Immutable selectors is another big one. If you're coming from an existing, well, like extensions v1 beta 1 or apps v1 beta 2 or beta 1, you can change the selector on one of these workload API objects, which will modify the pods that are selected and controlled by that controller. This also caused no end of havoc. There were many, many issues on GitHub where pods were orphaned. People experienced minor outages because they mutated their selectors. And while it does enable some interesting use cases, at the end of the day, we really felt that those use cases could be implemented by other features as well. And they could be implemented in a way that it wouldn't be potentially risky for our users. And honestly, taking an API to stable is all about making sure that we're shipping the right thing for our users and we're not shipping something that's potentially dangerous. We cleaned up the statuses of the objects a little bit, and we added status conditions to stateful set and daemon set. Even though we're not populating them right now, we think that in the future, conditions might be a way to communicate other interesting events about daemon sets and stateful sets to, well, users and various APIs. We got rid of the created by annotation in favor of controller ref. Created by kind of existed prior to garbage collection in Kubernetes. So after we added a full garbage collector, we had controller ref and owner references across the API. There really wasn't a need for created by anymore, and it didn't have any really valid semantics. We added scale sub-resources across the board, so there's uniform scaling with the exception of daemon set, which again, generally daemon sets create pods when you get a new node in. They don't create pods based on some scale that you provided them. We did not enable HPA for stateful set yet, which is a feature that we're aware people are interested in, but databases don't tend to scale in the same way that serving workloads do. So until we get custom metrics solid, we didn't see a lot of value in enabling horizontal pod auto scaling for stateful sets. Garbage collection is now defaulted to delete. And the primary difference there is currently the default is orphan. You wouldn't, if you use kubectl to delete things, you wouldn't actually notice this. It's only if you call against the API directly you would see this behavior. Well, what would happen is when you delete a stateful set, the pods in the stateful set wouldn't be deleted by default. We implemented a Reaper inside of kubectl to implement the delete semantic by default in kubectl, but we were able to move this server side so we can get rid of all that functionality and additional complexity in kubectl. And in 1.9, we did what we planned to do in 1.7, which is basically move the apps v1 beta to API to v1. Moved it wholesale, didn't make a lot of modifications, but it's available at GA stability now. Slide, please. So what does that mean? So GA doesn't mean that we're not going to add any new features or that the API is frozen and will never change. What it does mean, however, is that we're never going to break you. Any changes we make going forward are going to be backward compatible. This version of the API is not going to be deprecated, not in the near future. If there's a V2 at some point and then sometime in the very far future after that V2 is released, maybe we would consider deprecating it. But as it is, this is the final API and you can start building against it. In fact, all new code should go against this API. For existing code, now we're sensitive to the fact that we told people to go out and use deployment, use daemon set. In fact, we used it for our own cluster add-ons. We're not going to force you to get off of extensions v1 beta 1 tomorrow. We're not going to force you to get off of apps v1 beta 1 tomorrow. We'll be very sensitive to how we migrate people off of those and how we deprecate those APIs. In point of fact, they're actually all deprecated right now, but we are not removing the storage version, and we haven't even converted the default storage version to go to apps v1 beta 1. What you'll see in the future at some point is that extensions v1 beta 1 API objects would be not enabled by default. And that would basically be like you'd be required to implement some specific action to turn the API on at that point. That would be a good signal that we're starting to force the migration going forward. But as it is right now, we don't even have a plan going forward to force people off. You can kind of, to get to the stable API, do the migration as you see fit. There are bidirectional conversions implemented for all API versions to v1. So if you go to use the v1 API, it should not break any of your existing API objects. It's just, in effect, point your code from one endpoint to another endpoint. I believe that's everything. Are there any questions? No, don't see any. All right, thanks.
Right, thank you, Ken. So now we have the Q&A section. We had several questions in the chat, in the Q&A section on the Zoom interface. So yeah, so the question is probably to Michael and maybe to Saad is by Sadeep regarding the support for CSI as well for Windows. I'm not sure if I completely got this question, so maybe maybe it means that is there CSI support for Windows implementation in Kubernetes? Hey, Mike, you're muted.
Yeah, I don't think we've gotten that far yet. You know, we just barely got to support volumes and some of the other storage artifacts, so we haven't had the discussion about that for SIG Windows. Likely it's going to happen in the next couple of months. We just haven't gotten there yet.
Yeah, perfect. We have the question regarding workloads API to CAN. So workloads API is not GA. What does it mean on your previous slide?
You're looking, Ken?
Yep. Typo.
Yeah, I also expect that because workloads API is one of the major features for Kubernetes 1.9. It's really GA one.
Yeah, it's definitively GA.
Yeah, yeah. Right. So do we have any extra questions here?
There was one more question that was already answered. That's around one of the things I showed in my YAML file is designating the node selector that it's Windows. So if you have a hybrid environment with Linux and Windows, some folks are going to obviously have concerns about, do I have to go change all my previous YAML files for my previous deployments? So some of that can be changed through with the environment configuration in the scheduler. And some of the other problems we're going to have to solve in SIG Windows. So that's something that's actively on our table today, how to solve this.
Mutating webhook admission.
Yeah, nice. We also had one more question regarding CSI that has been already answered by Seth. So the question was, CSI looks somewhat comparable to Cinder. Yes, it's the similar idea, but lifecycle of CSI is designed with containers in mind. We also have yet another question. It's not really related to our today's topic, but it's the general Kubernetes question regarding what is the best GUI to deploy and manage pods. I can recommend to try the Kubernetes dashboard, the official Kubernetes project to manage Kubernetes clusters. All right, so if we don't have any other questions, thank you everyone for joining us today. Thank you our presenters for sharing your knowledge about the new features for 1.9, and hope to see you, all of you, at our next webinars. Thank you.